by Dr. Jia Guo. So Jia, I can introduce you, or maybe you can introduce yourself a bit of, about your background. What was your major, your undergrad, postgrad, and we are very actually lucky to have Jia with us as a postdoctoral researcher in our center. So she's working on a few exciting projects, including freight rail electrification. But I think today's talk is about freight rail scheduling for trainmen and engineers. So another interesting aspect. So without further ado, and for the online attendees, please just text your questions in the chat box because we can't hear you, unfortunately, for IT glitch. So Jia, would appreciate if you can introduce yourself to the team and then go over your presentation. Thank you.
Hello, everyone. Thank you for coming to my seminar. I did my bachelor in logistics and did my master's in operations research and PhD in operations research and industrial engineering in the University of Texas. And now I'm working as a research associate here on the freight rail electrification problem. And I'm very happy to be here. And today, I would like to give the seminar on the weekly scheduling for freight rail engineers and trainmen. So this study was conducted in collaboration with Professor Bard and the University of Texas at Austin. Okay, in today's presentation, I'm first going to give you a brief background and motivation introduction. Then we'll dig into the problem description. Then we'll talk about the methodology and look at the computational results. Finally, I'll give you the conclusions and discussions. Okay, first, let's look at the background and motivation. This study is based on the working status of the current U.S. freight rail engineers and trainmen. One very big motivation behind this study is that a lot of engineers and conductors complain that they do not have a satisfactory work-life balance due to irregular, unpredictable work schedules. Actually, there are not any working schedules for engineers and conductors. So it is very often that when engineers are enjoying time with their family, they receive a call from their supervisor asking them to drive for the next train in the next maybe 3 to 5 hours. Then they have to leave home and go to the train station to get prepared. In other words, people are on call 24 hours a day, 7 days a week. So there is no family life for people, for engineers. So in this project, our goal is to systematically construct predictable weekly schedules for engineers and trainmen who travel between two cities, like City A and City B. Specifically, we would like to develop an algorithm that produces schedules where all hours of service requirements are satisfied and company-specific rules and policies are adjustable. Also, our goal is to find a balance between trip under coverage and travel cost, because usually the higher the coverage rate, the more people we need. So there is always a trade-off between the trip coverage and travel cost. We need to find a good balance between the two terms. And finally, we would like to display the final schedules in a user-friendly manner, for example, in a good graphical and text format. Okay, then let's look at the problem description. First, I would like to give you a brief overview. As we discussed in the previous slide, our goal is to assign trips to engineers and trainmen with all the constraints satisfied and to find a good balance between coverage and travel costs. Our planning horizon is 1 week for now. Maybe we can expand it in the future, but for now it is 1 week. And each trip requires 1 engineer and 1 trainman to work on the train. Since the requirement for engineer and for trainmen are very similar to each other, in the rest of today's presentation, we're just going to concentrate on engineers because for trainmen, everything is exactly the same. And so in this problem, 1 engineer must choose exactly one of the 2 cities as his home base. So it should be either City A or City B. If a trip is not covered by any schedule or any engineer, then it must be covered by an extra board engineer or an e-board engineer. Since the cost of an e-board engineer is very, very high, we should avoid that. In other words, we should try to assign all trips to all engineers in schedules. During the planning horizon of 1 week, an engineer can leave home base for multiple tours, but he must start and end in their home base. As we can see from the figure, each tour starts and ends from the home base. When an engineer starts a home base, he can travel to somewhere else, do something, and then must come back. And during the entire planning horizon of 1 week, there can be multiple tours. Okay, then let's look at the procedure of one tour. In the upper figure, there is a description of one tour. At the beginning of each tour, the engineer is resting in the home base. Then he knows, well, there's a train departing very soon. Then he gets prepared and drive the train. And then after a few hours, he arrives at the away base. After he has arrived at the away base, he has 3 options for the next step. Option 1, he can choose to stay in a hotel in the away base and rest at least 10 hours, but at most 15 hours. After the rest, he can drive the next train back home. In the second option, he can wait in the away base for the next train, then take the next train back home. And remember, in the second option, he is not the driver in the next train. That means he's just a passenger, a deadhead. That's why we call the second option is a train deadhead. In the third option, he takes the van directly home from the away base. So since in option 3, he is also a passenger in the van, we call it a van deadhead. In other words, options 2 and 3 are both deadhead trips. So this is the operation of one tour. And as we have discussed, the duty of an engineer in the planning horizon consists of multiple tours. Okay, and then here let's look at some assumptions of this problem. If an engineer takes a train to home base from from the away base but not drives, then this is a deadhead trip. If he takes a van from away base to home base, this is also a deadhead trip, and the trip starts at the arrival time of the previous trip. And the deadheading to an away base is not permitted. That means deadheading is only allowed from away base to home base. Deadheading from home base to away base is never permitted. After an engineer finishes driving a trip T, he must do one of the following. In the first case, if the definition of trip T is the home base, then he must rest at least 10 hours in home. Otherwise, if the destination of trip T is the away base, then he has 3 options in the figure. An engineer can rest at either his home base or away base. Here are 5 status of an engineer. An engineer must be in exactly one of the status. He can be driving, resting, waiting, traveling on the deadhead train from the home base to from the away to home base, or traveling on a van from the away base to home base. All conditions are considered working except resting. Okay, now we have understood the operation of the train and the engineers. Let's look at the decision variables. That means, what are we supposed to decide? There are several sets of decision variables. The first set of decision variables is the home base assignment to each engineer. That means each engineer must be assigned exactly one city as their home base. The second set of decision variables is the trip engineer assignment. Each trip must be assigned to at most one engineer, and there is an upper and lower limit on the number of trips assigned to each engineer in a week. This is used to avoid overload or underload. Then we also need to decide how to make engineers return home from the away base. These are the 3 options we discussed before. And finally, we need to make decisions on the rest location and the amount of rest for each engineer. Okay, then let's look at what regulations are we supposed to follow. There are two big sets of constraints. One is general constraints, and the second set of constraints is the hours of service constraints. In general constraints, in addition to those we have just discussed, there is also an upper and lower limit on the fraction of engineers assigned to each city. For example, there must be at least 30% of the engineers assigned to city A, but no more than 70% of the engineers assigned to that city. We add this constraint because we don't want one city to be overloaded and the other city is totally empty. And also we require a duty to consist of at least 4 trips. This is used to avoid long idle time of each engineer. And duties are designed to be cyclical. That means they repeat every 7 days. For the hours of service constraints, we have working regulations, deadhead regulations, and rest regulations. For working regulations, we require that an engineer cannot work more than 70 hours in a week and cannot drive more than 12 hours in a row. For deadhead regulations, an engineer cannot spend more than 7.5 hours per week as limbo time. So this is the amount of time spent in waiting or staying in deadhead transportation, starting from 12 hours after the beginning of their on-duty period. Then the rest regulations include that an engineer must have at least 10-hour rest between driving every 2 trips. An engineer cannot rest for more than 15 hours in the away base. An engineer cannot rest for more than 3 days in a row, otherwise he is too idle. And there are 2 special rest regulations. One is if an engineer works 7 days in a row, then he must rest at least 48 consecutive hours after the 6-day work. Similarly, if an engineer works 7 days in a row, then he must rest at least 72 consecutive hours after the 7-day work. Then, what is our goal? As we discussed, we have 2 big goals. One is to minimize the undercoverage. The other is to minimize travel costs. Undercoverage means the number of uncovered trips. The travel cost includes several items, including number of engineers and number of data trips by van and by train, the number of times an engineer does not have 48-hour rest, and the number of hours rest in the away base. So we want to minimize all those costs. Since those terms are not similarly important, we can add a weight in front of each term to represent their importance. Okay, and then let's look at what are the parameters. What is known in advance? First, we know the penalty weight in the objective function, and this can be pretty subjective and can be totally decided by our own preference. And the working time, we have an upper limit on the number of on-duty hours per week, a number of consecutive on-duty time, a number of consecutive working days, and the number of consecutive days off. Then the rest time. There's a minimum rest time required between every 2 trips and the maximum number of hours resting at the away base. Also, we have the maximum limbo time per week, which is fixed at 7.5 hours in our computational experiments. Then I'll show you what are the final measures. What can we finally get from the algorithm? The final output consists of 2 levels. First, we have system level, and then we have engineer level. The output in the system level is pretty general, including the total number of engineers, the fraction of uncovered trips, the percentage of the percentage of engineers residing in each city, and the fraction of engineers with 48 hours off in a row. For engineer level, we concentrate on the average cost measure values for each engineer. Then that includes the schedule in the week, the number of deadheads, and the number of rest hours in the away base, the number of driving hours, waiting hours, deadheading hours, and the total on-duty time. Then some people may ask, why do we need optimization? Let me give you a very small illustrative example. Let's assume we have only 2-day planning horizon and only 4 trips. Those 4 trips have a lot of overlapping. So if there is no optimization at all, we may say, well, we might need 4 engineers to drive the 4 trips. However, after some optimization, we can see from the figure that we only need 3 engineers to drive the 4 trips, where engineer 1 can drive both trip 1 and trip 3. This can significantly reduce the labor cost. Okay, then let's see what the methodology is. We proposed a 3-phase algorithm to solve this problem. In phase 1, we use a random column generation. The phase 1 algorithm consists of 4 steps. In step 1, we construct a wide varieties of random feasible schedules over the planning horizon. Let me show you the construction algorithm. Okay, in the construction algorithm, we find that the length of each trip is significantly impacted by 3 factors. For example, it is impacted by the day of the week, the period of the trip, start time, for example, whether the trip starts between 7 a.m. and 7 p.m. or between 7 p.m. or 7 a.m. And it is also impacted by the origin of the trip. So we for each day of the week and for each period and each origin, we find the set of trips starting during that group, and let TBDP be the set of uncovered trips starting during that period on that day from that city B. Then we randomly assign one of the uncovered trips in that group. And then we find the next, for example, here we use ND as 6. We find the next 6 trips the engineer can drive from the away base to his home base. Then the next 4 train trips that he can deadhead from the away to home base. Or the next van he can take from the away base to home base. Then among the 6 plus 4 plus 1 potential trips, we randomly choose one as the engineer's next trip. And we repeat these steps until no more trips can be assigned to this engineer without violating any of the constraints. By using the construction algorithm, we can generate hundreds, even thousands of schedules in just a few seconds. Then, after we have a large pool of schedules, we use an optimization model to assign a feasible schedule to each engineer by solving an optimization model. And by the end of step 1, there are still some uncovered trips. Then we need to use step 2, the replace algorithm, to replace a deadhead trip with an uncovered trip if the resulting schedule is still feasible. Let me give you a small example. As we can see from the upper figure, we have one engineer, let's say engineer 1, whose home base is in A. This engineer drives trip 1 on Monday 10 a.m. and arrives at B at Monday 8 p.m. In the original schedule, he waits in B for 2 hours and starts taking B as a deadhead trip back home. Then he arrives home on Tuesday 8 a.m. Then he rests home and waits until Wednesday 2 a.m. to drive trip 3. However, there is an uncovered trip, which is in the gray box. The uncovered trip starts at Tuesday 6 a.m. from B to A. So then we can think, well, maybe we can replace trip 2 with trip 4 in the schedule of engineer 1. So we will replace it, and then the trip 4 is then covered by engineer 1. Actually, there is one other benefit of the replacement. That means we can not only reduce the number of uncovered trips, we can also remove the deadhead trip from the schedule of engineer 1. However, by the end of step 2, there are still uncovered trips. Then we use step 3, insert algorithm, to insert an uncovered trip between 2 successive trips if the resulting schedule remains feasible. Let me give you a small example. This example is very similar. So engineer drives trip 1 from A to B and waits in B and takes a deadhead train back home. He rests home from Tuesday 8 a.m. to Wednesday 8 p.m. As we can see, there's a wide gap between Tuesday 8 a.m. to Wednesday 8 p.m. And there is an uncovered trip from A to B starting at Tuesday 6 p.m. Then we think, why don't we insert the trip 4, the uncovered trip, to the schedule of engineer 1? We did so. So we allowed the engineer to drive trip 4 from A to B, and then in order to make him home and without getting by another train, we let him take van back home and arrive home at Wednesday 5 a.m. And still, he can rest for more than 10 hours before driving the next trip. That's trip 3. In this case, we can reduce the number of uncovered trips. Then in step 4, we remove some schedules with fewer than 4 trips because we don't want engineers to take idle for too long. Then in phase 2, we use traditional column generation to generate and select optimal schedules from the pool of all those candidates. Then in phase 3, we apply switch algorithm. We switch a trip from a schedule with more than 6 trips to a schedule with fewer than 5 trips if the resulting schedule is feasible. We do so because we want to find a balance in the work quantity of each engineer. Let me give you a small example. Okay, in the upper figure, we have 2 engineers, engineer 1 and engineer 2. Engineer 1 drives the trips in blue boxes, and engineer 2 drives trips in green boxes. As you can see, engineer 1 drives 7 trips, while engineer 2 drives only 4 trips. There is a very significant imbalance in their working assignment, which is unfair. Therefore, we switch trip 4 from trip 1 to engineer 2, from engineer 1 to engineer 2 to fill the large gap between the trip 9 and trip 10. Therefore, the workload will be more balanced between the 2 engineers. Okay, now we have a thorough understanding of the methodology. Then let's look at our computational experiments. Let's first look at the experiment design. We have 3 groups of baseline instances, each group for 1 city pair. In each group, there is a baseline instance and 100 random instances. We first solve the baseline instance for 9 times because the algorithm has some randomness in phase 1. Then we insert the baseline schedule into 100 random instances and compute the cost measures. In other words, we try to run some simulation based on the schedule from the baseline instance and see how the schedule works for the random instances. In the table, we can see the data. We have 3 groups. Group 1 includes instances 1 through 9. Group 2 includes instances 10 to 18, and instances 19 to 27 are for group 3. The number of trips in each group ranges from 132 to 207. The trip length by van is pretty short. It is between 3 to 5 hours. And the average trip length is between 8 to 9 hours. To account for the randomness, we increase the trip length by alpha, which is a percentage. So alpha can be 0%, 10%, or 20%. We're going to show that in the rest of the slides. Okay, in the output analysis, let's assume all the alpha values are fixed at 20%. So in this table, we show the cost measure values for both baseline instances and the average of 100 random instances. As we can see, the first 3 cost measures, the number of engineers, average number of driven trips for each engineer, and the percentage of trip coverage rate are same for both baseline instance and the average of 100 random instances, while other cost measures are slightly different for between the baseline and random instances. Let's look at them one by one. First, let's look at the trip coverage rate. The trip coverage rate on average is about 97.33. So for all the three groups, the average value ranges from 95.99 to 98.01, which is pretty high. Then let's look at the delay condition. In the baseline instances, there is no delay. However, in the random instances, about 12.5% of the trips are delayed. Among all the delayed trips, the average number of delayed hours is 1.73. Then let's look at the average number of driven trips assigned to each engineer. In all the instances, each engineer drives 4.62 trips on average. However, in group 3, that is from instance 19 to 27, the workload is much lower because the demand is unevenly distributed among over the planning horizon. That's why it is very hard to assign one engineer a large number of trips. But on average, the number of trips for each engineer is about 4.62. Okay, then let's look at the train data trips. As we can see the comparison between the baseline instance and the average of 100 random instances. So the blue curve represents the baseline instance, and the red curve represents the average of 100 random instances. The two curves have very similar pattern, but the blue curve, the baseline costs are slightly higher. So on average, each engineer in the baseline instance takes 0.1755 train data trip on average, and in random instances, each engineer has 0.1551 train data trip. Oops. And then let's look at the van trips. The van trips between the baseline instance and random instances are still very similar, but the random instances have a slightly higher value of 1.9582, while the baseline instance, the random instance has a slightly higher value with 1.97. And then let's look at the average number of 48-hour consecutive rests for each engineer. In baseline instances and random instances, there are 62% and 64% of engineers having 48-hour consecutive rest. That means 46% of the engineers in simulation can have 2 days rest in a row. Then let's see the average number of rest hours in the away base. Still, the two curves have similar patterns, but the values are kind of, the difference of the value is kind of large. In the baseline instance, each engineer has 2.5 hours fewer than the random instances. And in random instances, each engineer rests 17.72 hours in the away base. Then let's look at the driving hours for each engineer. In random instances, each engineer drives 37.48 hours. The total on-duty hours for each engineer in random simulation is 47.3 hours, while in baseline schedule, each engineer is on duty for 52.91 hours. Okay, then we conducted a sensitivity analysis on alpha, which is the increase in demand. As we can see from this table, the first column is the name of cost measure. The second, third, and fourth columns are the difference between the baseline cost and the random cost. They're They're based on the condition of alpha being 0%, 10%, and 20%. The closer the delta value is to 0, the better the simulation is. For the last column, it is the p-value from the ANOVA test. If the p-value is less than 0.05, it means there is significant difference among the different alpha values. As we can see from columns 2, 3, and 4, when alpha equals 20 works best to simulate the number of train deadhead trips and number of deadhead trips by van and the delay conditions and the number of train deadhead hours and the number of deadhead hours by van. When alpha equals 0, it works best to estimate the number of 48-hour consecutive rests, the number of rest hours in the away base, and the number of driving hours, waiting hours, and the total on-duty hours. The last column shows that all p-values are smaller than 0.05. It indicates that there is significant difference in delta among different alpha values. Okay, let's come to the conclusions and discussion. In this research project, we investigated the freight rail scheduling problem to decide the home base of each engineer and assign trips to engineers, construct weekly schedules, and considers federally mandated hours of service regulations. We achieved our goal to maximize the trip coverage, maximize the number of engineers with 48 consecutive hours off, and minimize the train and van deadhead trips and minimize the number of rest hours in the away base. To solve the problem, we developed a 3-phase algorithm and find high-quality solutions. In our solution, we achieved a high demand coverage of above 95%. For each engineer in the baseline instance, the number of deadhead trips by van was between 0.04 and 0.44. The number of deadhead trips by van was between 1 and 3. The number of rest hours in the away base was between 13 and 17.3. About 62% of the engineers enjoyed 48 consecutive hours off per week, which is very engineer friendly. And the percentage of delayed trips in the simulation ranged from 9% to 17%. The number of delayed hours for each trip was 1.48 to 1.94. Despite the promising results of the algorithm, there are still some limitations that we can address in future research. For example, we can consider the preference of engineers and treat workforce as distinct. Then we can allow engineers to choose their working days or time windows in advance, which will provide them with more flexibility. And finally, we can expand planning horizon to 2 to 4 weeks, design tours among 3 cities, and address randomness in departure times. Thank you.
Okay, great. Thank you so much. So let's see if there's any question. Thanks, Jia, for yeah, Anissa, go ahead.
Yeah, thanks for the presentation. I want to ask about what are you trying to highlight or inform us with comparing the baseline and the instant graphic?
In what?
In the result, comparing the baseline trip and instant trip. Is it?
Comparing the baseline and instance.
Yeah.
Oh, yeah. So actually the baseline schedule was obtained from the fixed set of data set. Since in reality, there is a lot of randomness in the schedule. For example, the trip lengths are not fixed. The departure times are not fixed. That's why we use random instances to simulate, to test how efficiently our generated schedule is. So we insert the baseline schedule to the random instances and calculate the cost measures and compute the average values to see how the schedule works.
So, Mian, go ahead.
Thanks. Good work. I also didn't fully understand. Can you tell me more again? Maybe I missed it, but what is the random? What your instances are? What does each instance look like? Is it a 1 day, 1 week, or can you tell me more about it?
It is 1 week
1
planning
week.
horizon. So one instance means so for one baseline instance, we have a lot of trips.
How
These
many trips in each instance? Number of trips per instance.
That's like 100.
yeah, for 132 to 207.
Okay.
Yeah, depends on different city pairs. So for each instance, we have fixed trip departure times and fixed trip plans.
Sure.
So we apply our algorithm to assign engineers
Yes.
to those to drive those trips, and then we have a schedule for each engineer. Then we insert this schedule.
So what was random instance then?
Random instance is we assume that the trip lengths are not fixed.
Oh, it's just the trip length,
Yes,
nothing else.
Yeah.
Departure time.
they're fixed.
Oh, they're fixed. Okay.
So just the trip length is okay, got it. Yes, the trip length.
Because it's freight rail, it has to give way to passenger trains.
And in the objective function, so you had summation of two terms, right? You said we do a weighted
Weighted
sum.
cost.
Yes.
Right?
Actually, a lot of terms, but two bit terms.
Yes.
Yeah.
A typical question that you probably get from any.
How to assign the weight?
Yeah, how do you come with those weights?
Well, it could be very subjective, but one thing is we can, based on the length of the trip, we can estimate about how many trips an engineer can drive. For example, we know an engineer must rest 2 days a week. And then, for example, each trip is about 10 hours on average, and he has to rest at least 10 hours after each trip. Then we can estimate at most how many trips one engineer can drive in a week. For example, he can drive 8 trips at most. Then we would make the quotient between the number of trips, the quotient of the weight for the engineers and the number of uncovered trips to be 8, because one engineer can drive 8 trips. That can be very subjective, but this is one way for us to estimate it. And the number of deadhead trips and the number of deadhead trips by van and by train can be obtained by the cost of van and the cost and the time cost of the deadhead train. For example, how many hours an engineer must get paid, how much an engineer must get paid for each hour. So that can be transferred financially from time to money. And then we can combine the train and the van issue to calculate the weight.
One last question.
Yeah.
So you talked about the horizon, and that is 1 week.
Mhm.
You didn't do multi-period planning, so you plan every week independently, right? Or is it multi-period?
The rolling.
Yeah, it's a weekly cyclic problem. So we assume where did I write it? Anyway, we assume the schedules are weekly cyclic, so they repeat every 7 days. So every Monday, the engineer schedule, this Monday, my schedule is exactly the same as my last Monday. Yeah, we assume it is cyclic.
It repeats.
Yes, every 7 days.
Does it have to repeat, or your second week or third week could look different than the previous week?
For
Why
now,
is it fixed?
because we assume every week the train schedules are
Oh,
very
the train
similar to
schedule
each other.
also, is in reality, does the train schedule also?
Sometimes it changes.
I see.
Yeah, but for now, we assume they're There.
Because again, in many problems like this,
Uh-huh.
again, a question that we usually ask is, why didn't you consider
Sure.
multi-period scheduling or
Yeah.
whatever you're optimizing? Then you have really multiple periods,
Yeah.
and every week doesn't have to look like the same as previous, and would actually depend, but not necessarily exactly the same.
Yeah, actually, if the train schedules are very similar each week, then we make it weekly cyclic.
Yeah.
If they're not same, then we plan the schedule by right before the beginning of each week. So we can choose either one of them. But in the future, yes, you're correct. It is very essential for us to expand the planning horizon to 2 weeks, 3 weeks, and even for like a quarter of the year, because some are seasonal.
Another question came. Do we
Yes.
have time for another
Yes,
question?
please. Go.
So given your object, can you go back to the objective
Yeah.
function?
Uh,
Yeah, another difficult question. Who is the decision maker in this scheduling? Are all those variables you include in your objective function come from a single decision maker, or are there multiple decision makers that you don't necessarily incorporate, that they're actually independent, not necessarily independent, but separate decision makers that feed into your objective function?
that should be made by one single person.
Should be, but in reality, what is it? Is it one really, or does it come from different?
It is one.
One.
It is one. Yeah.
Yeah, I think in many similar scheduling problems for either it could be, drivers of camper vans, because I know that because my husband actually works as a scheduling analyst for camper vans or Polo motorway, and for train and for buses, there's actually a software decision support system that it has all of the, trip requests, the number of available drivers, origin, destination, 2 cities, trip length, departure time, and then you optimize it. So I reckon that it's just kind of simulating the centralized decision
I know,
making.
but usually from what we learned in even if you talk with
Yeah.
some, let's call them route planners or schedulers,
Mm.
they get feedback from the drivers. So you get feedback from the engineers, and you actually have to incorporate some of their preferences
Yes.
in the optimization. What do you think about that? Like, how do you?
Adaptive planning, adaptive rescheduling.
Actually, I haven't heard back from engineers since I gave them the schedule, but what I know from them is that they are very angry about lack of schedules, because for now they don't have any schedules.
And it was for US class 1 railway, freight railway.
Yeah.
Good.
We don't know how actually it works in Australia, but
And everything was deterministic in your optimization, right? You didn't have
Yes.
a stochastic element.
Right.
so was there any client for this project?
The
Client?
Federal Railroad
The
Administration,
Federal Railroad Administration,
Yeah, the-
US Federal.
managerial level.
Right.
Fantastic work.
Thank you.
Just yeah.
Thank you for your presentation. I just have one question.
Yeah.
If this one used in China, every school schedule in the station work for the engineers and trainmen are controlled by a railway management center. They will give the station work schedule. So I just want to know if this one is adapted in just like China. Is there conflict? Did you consider any conflict with your scheduling and with the railway station management?
I think so, because I think one important aspect is the under coverage, because China has a very large population, and there's, this is for freight train, and it has a high demand for like cargoes. If there is under coverage and people need something really badly, even if we assign it to extra board engineers, the value, I mean, the cost will be really high. If we cannot afford the e-board engineer, the receivers will be faced with a lot of problem that can bring us a lot of financial damage. So that is one of the conflict I can think about.
Thank you. And one more question is about the model, because we didn't see your visualization of the model.
Oh, yeah.
You have to mention the system level and engineer level. What type of the model is it? Did you do the optimization the same or just one by one? And is this a single level model or 5-level model? It's a non-linear model or linear?
Okay, let me show you. So first we construct a wide varieties of random feasible schedules, and we have seen the construction algorithm. So by this algorithm, we create hundreds and thousands of schedules. Then we go back and we have a large pool of schedules, and we use this model. Sorry, it's a screenshot from my paper. I didn't type it myself. So I simply got the snapshot from the paper. So we use this optimization model as the restricted master problem. And in this model, we have two sets of variables. One is UT, which means it is the uncovered trip, and lambda BS. Lambda BS is 1 if the duty S is selected or schedule S is selected for an engineer whose home base is in B. So this is a mixed integer linear programming model. By solving this model, so here we give a weight of alpha D to the under coverage and give the CBI as the cost of giving schedule S to the engineer whose home base is in B. So we want to minimize this objective function. Okay, thank you. And then here we define the under coverage. And this here we try to assign each trip at most one engineer. Then in this one, for the covered trips, we do not assign any engineers. We do not assign any schedules to that trip. And in this one, these two, FU and FL, are like 70% and 30%. That means the upper and lower limit on the fraction of engineers assigned to each city. So we, by using these two constraints, we restrict the fraction of engineers to each city. And then here are the definition of the variables. So by solving this model, we can select the so-called optimal schedules from a large pool.
Thank you.
Thank you.
Okay, no more question? I don't see any question online. Just everyone actually thank you, Jia. Okay, so with that, then let's just put your hands together for Jia. Thank you so much for presentation. And please just consider volunteering for the next rCITI seminar if you have any prior research, anything even like ongoing or even just research ideas. The launch time of Fridays is just for us to bounce back ideas and brainstorm and present it to us. So it's just like a casual setting. And thank you so much for everyone also joining us online and also in the room. Thank you. Thanks everyone. Thank you, Jia.
Thank you.
Thank you. Great. Okay, so I stop sharing.
Thank you for your help.
Thanks. So let me start recording also.